Okay, last time we talked a lot about the value of PSA, the threshold for percolation models, right? So here in this video, I want to start with another concept. It's called phase transition. Okay, a phase transition point is a point at which a system's properties change abruptly. Okay, and you can tell that when p-value is very close to PSA, or you can say when p-value is equal to PSA, the percolation models, they are at this point of transitions. Okay, the parameter values at this occurs are known as critical values, PSA, right? For example, and percolation properties that change at its critical values, right? First one, probability that a randomly selected site belongs to an incipient infinite cluster, a very large spanning cluster, right? A very large cluster when percolations happen on an infinite lattice. So on a limited lattice, which means there are size, we call it spanning cluster because they connect at least two sides, right? If there is a lattice that has infinite size, obviously there is no spanning cluster because there is no size. There is no size. So if that is the case, we call it incipient infinite cluster, right? A large cluster. And also the average cluster size changes abruptly at PSA, and also correlation length or cluster length and the fractal dimension of spanning clusters. Okay, and let's get back to power laws. Power law, we discussed about this in random walk model, right? It means that a relative change in one quantity results in a proportional relative change in another or in the other quality. So here is cluster size versus number of clusters of size equal or smaller than S. So here, where is the change in one quality? In one quantity results in a proportional change in another quantity. So here, for example, cluster size. When the cluster size is 10 to the power of 4, how many clusters are there? 1, right? Remember, this panel is at it is at the point that P is equal to PSA, okay? So when the size is 10 to the power of 4, there is only 1 cluster. So when we decrease this size by 100 times, which means that currently the size of cluster is 10 to the power of 2, which means 100. So the size of cluster decreased by 100 times. So how many clusters are there? Now it's 50, which means that when the size of cluster decreased 100 times, the number of clusters increased by 50 times. So this is a proportional change in the number of clusters when the cluster size changed proportionally, right? And we know that these two parameters, cluster size and number of cluster size, and number of clusters of size equal or smaller than S, these two variables, these two parameters, they are following power law. Their relationship is following powerful law. And when there is powerful law distribution, there are certain properties we need to be careful with. The first one is that the data set lacks of well-defined average. What does it mean? So let's talk about the purpose of average. Average or mean is designed for what? To show the central tendency of a data set. Where is the center of the data set? Okay, since there is this lack of well-defined average, it means that if this data set is following power distribution, average, the definition of average is not that good. which means that in other words, average is performing poor, showing the central tendency of this data set. I'll give you examples later, okay? The next property is that there is something called universality, which means that you use a group of parameters. You can use some very representative formulas, mathematical formulas, to describe this distribution. Okay, examples will be provided later. But now let me give you an example of power law and why we want to use log-log plot to show power law distribution. Okay, for example, here is a curve between annual income and the population. Okay, so let's just say in dollar, right? So $50,000 as annual income is a very common value, right? Most people, they have an annual income around this value, and a lot of people, they have an annual income well below this value. Okay, so vertical axis is for population, and or you can say number of people with a specific annual income, and the horizontal axis is for specific value of annual income. Okay, as annual income increases, less and less people are with that value, right? If it is 100 million, if it is 100 million as annual income, not a lot of people have that annual income, right? So that's the reason why you can see that this curve is pretty high at the very beginning, because most people, they have very low yearly income, and as yearly income value increases, there is a huge drop in population, and maybe when you're talking about 100 million annual income, maybe less than 1% people can have that. So we have a huge tail on the right side of this curve, of this distribution. So here we have a very long tail on the right side, and here you can expect, if you increase the value continuously, there will be still super wealthy people who will have larger and larger yearly income. And in order to portray this relationship between population and annual income, you are going to use a very huge plot to address that, which is very inefficient. So the method here is to calculate the log value of all those values along x-axis, and also the values on vertical axis. After that, you're not having value versus value plot. You're having log value versus log value plot, which is this straight line on the right side. It is a straight line because the two parameters, the two variables you're trying to show in this log-log plot, they are following power distribution. If they were not, your curve here should not be a straight line. Now, for example, of course, on the right side, this is not the exact log-log plot for the plot on the left side. It's just an example. But you should know, if you have a perfect straight line in a log-log plot, then you can tell that these two parameters, these two variables here on a horizontal axis and vertical axis, they are what? They're following power law, or their relationship is following power law. Okay, so log-log plot is simply a very convenient and efficient way to address two variables which are following power law. Okay, so here I have even more examples. On the left side, we have temperature versus the number of cities. Okay, so vertical axis is for the number of cities, or you can say frequency. The horizontal axis is for the annual average temperature. Obviously, these two variables, they are from United States. Okay, mean temperature and number of cities with that mean temperature. Obviously, here we have generally a normal distribution, and we don't have very long tails on either side of this distribution. So this is not a power law distribution. On the right side, we have two variables here. The first variable is the population of cities. It is along horizontal axis. On the other hand, we still have the frequency of city or number of cities along, they are addressed along vertical axis. Okay, so here we can see that most American cities, they have a population somewhere between 50,000 to 100,000, right? That's the majority. That's the reason why we have a very huge, very long bar here, right? The middle part of this plot has been hidden because if you don't hide it, this vertical axis would be pretty long, okay, because it's linear, 10, 20, 30, 40, until 700, okay? So you can say there is this hidden part of the plot. On the other hand, we can say that some huge cities, they have what? 7.6 million population or even more. For example, New York, Los Angeles, Chicago, right? They are outliers and they are on the far right side of this population axis, which means that if you draw a curve for this plot, this curve will have a very long tail on the right side. Obviously, these two variables, population and number of cities with a certain population, they are following power law. Okay, on the right side, we have Gaussian-like distribution or non-power law distribution. On the right side, we have something called Paretian-like or power law distribution. Okay, so you can see the difference here. You can see the difference here. And why average is a poor is not very well defined for power law relationship. On the left side, we have a curve for what? The temperature, and B is the population of US cities. Okay, but here the vertical axis here is for temperature. Okay, and along the horizontal axis is the number of cities with a specific average temperature around the year, every year. Okay, so here, because the distribution here is non-power law. Okay, so if you calculate the mean of what? Of cities, you can see that the average number of city is right here in the center of this plot. Okay, so it means that averagely around 400 cities, they have a mean temperature, yearly mean temperature of 20 degrees. So mean is a good description because mean should be used to address the center of the data set. Here is generally the center of the data set. But on the right side, if we are talking about the population distribution of United States, mean is a poor distribution because most cities, they're on the left side of the mean. Only very limited number of cities, they're on the right side of the mean. So here is not actually the center of the data set, it's far left. It's on the far left side of this data set. Then you would say, wait, then what should you do? What I should do? I still want to find out the center of the data set. But I mean, average obviously is not a good option here because my data set is following power law distribution, power distribution, you should use something called median, okay? Which means that you should just rank your data set ascending or descending and find the 50 percentile from your ranking result, and that should be used to address your the center of your data set. Okay, use median instead of mean to do that if your data set portrays a power law distribution. Okay, so poorly defined mean, that's the first property of a data set if it is following a power law distribution. And another property when P is equal to Pc in percolation system is called universality. Okay, it turns out that all percolation systems can be described by a small set of universal critical exponents that depend only on system's dimension. Okay, so first one, probability of belonging to an incipient cluster, or if you are talking about a finite lattice, it's not incipient, it's spanning cluster, right? This probability is related to the difference between P and Pc to the power of beta. Okay, we're going to talk about beta later. Beta, gamma, nu, they are defined here, okay? And also average cluster is also related to the difference between P and Pc. Correlation length, or you can say the general length for clusters, it is also related to the difference between P and Pc. Okay, so right now, if your percolation system is having a having a value of Pc, your P value is equal to Pc here, then it's 0, 0, and 0. So when P is equal to Pc, it's a very special state for your percolation system. And we have beta, gamma, and nu. They are some universal critical exponents. Okay, and we have some results for them. Beta is usually equal to this value. That's a value for gamma, another one for nu. These values, they are settled, they are constants, regardless of the detailed geometry. That's why it's called universality. As long as you are looking at a percolation system, you can address these three parameters using P, Pc value, and beta, and gamma, and nu. Okay, these three formulas, they are universal. That's why there is universality. Okay, so yeah, let me show you some examples for ordinary percolation. The first one is called the lost ant. This is a very simple model for simulating flow and spread through percolation systems. Of course, here the word ant is metaphorical. It could be anything. It's just an agent. Okay, so but we use ant because we can imagine that an ant is trying to move on this lattice. Okay, some part of this lattice is occupied, or you can say is empty, so the ant can move between this empty sides. But if a specific side is blocked, of course the ant cannot move in, right? So a lattice with sides occupied with probability P, occupied sides can be used for the ant to move in. Okay, the ant can move into occupied sides. Okay, ant starts in a randomly selected occupied cell or site and can move only in one of the 4 cardinal directions, which means Van Neumann neighborhood. So we have 2 types of ants. The first type is called blind ants. Select one of the 4 neighboring locations at random and then move there only if it is occupied. Okay, which means that this blind ant could just choose a neighboring site that is unoccupied. If that is the case, then this ant will stay where it is right now for next step and choose again until an occupied site is chosen. Then it will move there. So you can imagine that the walking efficiency of a blind ant is pretty low because it could just choose an unoccupied site and it will not move after next step. There are also myopic ants. They select only from neighboring cells that are occupied. Compared to blind ants, they are much better because after each selection, the site that has been selected must be occupied. So it is sure that there is always a move, there is always a step out after each tick, right? So what distance will the ant travel as a function of time? How is this distance affected by P? Okay, so there is this model in the text model library. Okay, you can play with it a little bit as usual. And here is the interface of that model. Obviously, you can use multiple ants at the same time. Okay, you can change the p-value, myopic or blend, right, and number of ants. Okay, and on the right side there are different plots, right? The mean distance. So the horizontal axis is for time. The vertical one is for the distance traveled by these ants. Black one is the mean distance from calculated from all ants. Obviously, it changes across time by time. Red is the median distance, right? Mean and median, they are both for the central tendency of the data, right? If which one to use depends on the specific distribution of your data set, right? And we also have two gray curves, the upper one, the lower one. The upper one is +1 standard deviation of distance because you have mean value, right? You can calculate standard deviation after each step for distance. The upper one is the curve for +1 standard deviation from the mean, of course. The lower one is the -1 standard deviation curve from the mean. Okay, so let's see the statistics. So here we have 1, 2, 3, 4 types of simulations. Okay, with different p-value. Okay, with different p-value, and for all of them, these ants, they are all blind ants, which means that they could choose a location that is not occupied, so it doesn't move. Next step. So you can say for p is equal to 0.5, ants are trapped locally. So you can say that this is time. Horizontal is for time, vertical is for distance. The meanings of this dashed lines, solid black line, and dark gray lines, they are +1 standard deviation, -1 standard deviation. Black one is for mean. The dark gray one is for median, and the rest gray curves, they are for multiple simulations of ants. So you can see that these ants, they cannot travel very far. Most of them cannot travel further than 20 units away after 1,000 steps. Okay, which means they are trapped locally. Two reasons. Firstly, they are all blind. That's reason one. Secondly, the proportion of occupied cell is just too low. There is only half cells occupied, so they cannot travel too far. But obviously, we have an outlier. We have a very strong and lucky ant. He traveled so far away, more than 40 units away. Obviously, it is the winner of the community, right? This curve is is far beyond other curves, right? So when P is equal to PC, we have a sublinear diffusion, which means that the efficiency of the movement is not still too high, but better than the scenario with P equals 0.5, right? You can say that a lot of ants, they can travel longer than 20 units, right? And you can tell from this histogram. For this histogram, the horizontal axis is for the distance traveled. The vertical one is for frequency, or a number of ants that traveled that long distance, right? So you can say the difference here, right? At least a lot of more ants, they can travel between 5 and 10, but much less ants can travel between 5 and 10 if p-value was only 0.5. So you can just follow this logic and to increase p-value dramatic, one step, continuously. So this should be 0.59, right? That's a PC value. You increase it to 0.7, more ants, they can travel even longer, right? So we can say that the majority of the ants can travel from 5 to 20 units, much longer than this situation, much longer than this situation. And if you continue to increase P, do you think that these ants, they are going to travel even longer? No, that is not the case. If you change P to 1.0, it means that the whole space, the whole lattice has been covered by occupied cells. In that scenario, each ant, they are moving following what? They are Brownian motion particles, which means that it's a random walk. It's a random walk because all cells they're occupied. It means that at each step, choose one of 4 cardinal directions and move there. Right? It's a very basic random walk. And if that is the case, you can say, surprisingly, the majority of the ant can travel less further than the situation with p-value equals 0.7, because now they have the total freedom to go anywhere, but now they are less purposeful, which means that they cannot travel very far away compared to the situation where they have some limits when only 70% of the lattice was covered by occupied cells. So you can say there is not this simple positive correlation between p-value and distance travel, right? Because when p-value is extremely large, very close to 1.0 or even equals 1.0, all those ants, they cannot travel very too far away. A better option for longer travel distance might be 0.7 instead of 1.0, okay? This is what these 8 figures are trying to tell you, okay? The relationship between p-value and the distance traveled by ants. Okay, I will just stop here, and in the next video, I'll start with fire propagation. Okay, thank you.